the time. I'm realizing that's about all I do anymore when I'm here. And that's all you do. It's not good. So, if you want to get up and walk around the room, feel free. I was telling Mr. Chase I need to get a treadmill desk. I could just sit up here and teach at my treadmill desk and walk the entire time. So this thing is called the Sisyphus Train. And let me put this picture up here just in case anybody's watching the stream. Oh yeah. So this is the Sisyphus Train. Based on the name, you might be able to guess what it does. And even if you don't understand, if you don't recognize Sisyphus, you still might be able to tell from the picture. Adwin, do you know what the Sisyphus Train is or how it works? Or
Well,
what do you
not
think?
necessarily, but I do know Greek mythology.
So tell us about
And so
Sisyphus.
Sisyphus was a dude who the Greek gods got mad at. They do that a lot. And his punishment, I forget what he did honestly, but his punishment was that he had to push a rock up a hill. The problem was every time he got to the top of the hill, the rock would roll back down. And so he just kept going and going, going, pushing it back up the top of the hill and having it come back down.
I get him mixed up with the guy who was up to his neck in water and had some grapes that were just out of reach. Wasn't there some other character who was
I think that one's Tantalus.
Tantalus? Yeah, yeah. All right. So here's the. I've got a link to that. This I think it tells us what he did here. No, it just says he's a sinner condemned to Tartarus, notorious as the most cunning knave on earth. Still no specifics. Huh. Apparently he did some bad things. And there he is rolling the boulder up the hill. So back to the picture of the Sisyphus train. Does that give anybody any ideas about what this train does? It's called that because it is a lot like Sisyphus. And if you look, this looks like probably California. I don't know. It's somewhere out in the west. We've got a bunch of windmills in the back. Related to the windmills. And actually I would say it might be even more related to solar, but to windmills too. What's one of the problems with powering cities and just the grid in general with windmills?
Store the power somewhere.
Yeah, so when the wind's not blowing you don't have power, right? So you need some kind of storage solution. Same with solar. You can't use solar power at night unless you can store it. So the Sisyphus train stores the power. How?
Doesn't it recharge itself somehow?
Sort of. It never really charges up at all. You know, it's not like a battery that loads up with a bunch of charge. We'll get into charge later on. It's not millions and billions of coulombs that are of charge stored up in there, but it is taking the energy from these windmills and storing it. Guess how? Like Tantalus. Tantalus stored energy in that boulder every day. When he did what? Oh, not Tantalus. Tantalus was the grapes. Okay, Sisyphus. How did he store energy in the boulder? When did he put energy into it? When it rolled down the hill or when he pushed it up the hill? Pushed it up. So that's what this does. This is powered by, it could be powered by anything, but probably powered by these windmills. They create electricity. The electricity drives this thing up the hill farther and farther and farther and farther and farther. And once it gets to the top, I guess that's the end of it. But when the wind stops blowing, then they release this train and the train goes down the hill and then it generates electricity. So most motors are generators in reverse, and most generators are motors in reverse. So if you have a really heavy object like this train, and you move it up the hill, and then you can use it going down the hill to generate electricity, it's a good energy storage possibility. All right, in the context, so 1 and 2 are related. Number 3 here is not really related, but it's a term I want to throw at you. In the context of physics energy problems, I don't even know I'm asking you this now, but I'll go through with it. Some forces are called conservative, and others are referred to as non-conservative. Can you guess the difference between the two? And I've got my little thing here that says probably not, but what do you think? Any ideas between a conservative force and a non-conservative force? The definitions for this are not really great. If you
Does
look,
one like, well, does it, because does it something always, like, would the rock necessarily like store energy as it's going up? Does it have to do with storing energy?
yeah,
Like,
it does. So when the rock is going up, gravity's doing work, and gravity is a conservative force. So when a conservative force does its work, the energy is not lost. The energy is conserved. So you can push a rock uphill, and it'll still have the energy in it. It'll just be a different form, and then you can let it go, and you can get the energy back out. So gravity is a conservative force. Springs are conservative forces if you've got a really efficient spring. Magnetism can be a conservative force. These are all things that if you push against them, you put energy in, but then if you let go, they'll bounce back and they'll give you the energy back. That's kind of an easy one. Oh, an easy one to define. Non-conservative forces, one way to look at those is they're the opposite. You might put some energy or do some work with these forces, but then you don't get all the energy out that you put into it. And friction is an example of that. If friction is doing some work on an object and then it stops, you don't ever get that energy back. That energy leaves the system. But I think for me, a better definition of a non-conservative force is one that's outside the system, whatever it is. We're going to go over the law of conservation of energy today, and it basically says that the mechanical energy inside a system is finite and constant. You can like change it from potential to kinetic or kinetic back to potential, but the total amount is always going to be the same. But when there's a non-conservative force, that's something from outside the system either adding energy to everything or taking energy away. So non-conservative forces are forces where the law of conservation of energy doesn't really work anymore because its total amount is not constant. I don't know why I threw that in there. Return some stuff. I returned some stuff. Already did that. Finish these notes. So let me give you a preview of the week first. Today, we're going to do a little bit with, there's this roller coaster problem I meant to get to right before break, but I never got to that. And then, so we're going to do that. Tomorrow, anybody who wants to retake the test in the blue group, you can retake the test. So we'll spend just a little bit of time going over the homework. Any questions anybody has, you'll have some homework tonight. We can go over that tomorrow and then retake the test. You can either do the multiple choice section or you can do any page of it. There are 4 pages. You can pick any page you want. Then on Wednesday, a little bit of notes on springs and stuff, and it looks like some more homework. Oh, and also I'm giving you homework tomorrow night. So there'll be homework tomorrow night after the retake. It's basically just more practice problems. Thursday, the retake for the gold people, and then a practice test, Mr. Pennington's old test. And then Friday, we'll get into bungee jumping a little bit. We're going to do a bungee jumping activity with eggs next week, where the goal is to measure the forces on a bungee, and after you've measured the bungee, then calculate for an egg of a certain mass, if you dropped it from the ceiling, how far would it fall before bouncing back up? And you'll have to put a board underneath it as close to it as possible without breaking the egg. Actually, it'll be a tile, a ceramic tile that I've got, super hard. So we break a lot of eggs that way, but whoever gets the closest will get some donuts. Unless you don't like donuts or you like, no, not lactose. Gluten-free, I'll come up with something for you. Always some gluten intolerant people. So that's it for this week. And going back to today, Oh, let me just remind you about the homework. Blue, retake tomorrow. There's a practice quiz that we're going to start working on today. That's homework. And then I've got a couple of videos here for you. There are 2 problems in the homework, but each of those has multiple parts. There's a video for problem 1 and a video for problem 2. And this is also in Google Classroom. All right. Switch to, so get out your packet if you have it. If you don't have the packet, I've got a few more over there. Some people haven't picked them up yet. And I think before I really jump in here, I'm going to just review a little bit stuff we did before break, because you might not remember that at all. So we went over the definition of work. Work is a force multiplied by a distance, and the big W, that represents work. Unfortunately, little w represents weight, and the big W is also the unit for watts. So there are a lot of W's. The unit for work is joules. It's also the unit for energy. And one of the important things about work is that if you're going to calculate it with force times distance, if something is moving this way, you've got to use the component of force in the direction of movement. So in the example of this wagon here, if you pull it in this direction, and you apply a 20 Newton force, you can't multiply 20 Newtons by this distance. You have to figure out the component of that that's in this direction. Power is the rate of work, so it's just the work over time. And so if this 40 joules of work was done in a second, that'd be 40 watts, 40 joules per second. It's just work divided by time. And then we got to energy, but didn't really get very far with it. The work energy theorem, I'm not going to go into it deeply, but somehow, sometimes, this confuses the heck out of me. I mean, it's simple if I just explain it simply by saying, if I do some work on this pen right here, by applying a force over a distance, then that pen's going to gain kinetic energy. So, and the change in kinetic energy, the amount that it gained, is equal to the work I did on it. It gets complicated, though. It's pretty simple on the surface. This is the formula for kinetic energy. If you want to figure out where that came from, you can look in the online textbook if you're interested in the derivation of it. But I think that's something we're so familiar with, I don't need to derive. This is just talking about the relationship between food calories and joules. And it seemed like there was something else there. I don't know. Potential energy. Potential energy is mgh, mass times gravity. It's basically your weight times the height at which the thing is stored, or whatever it is. And then energy conservation, we did a little bit of this. This is the general case that just says all the energy you have is constant. Your kinetic energy plus your initial potential energy is equal to the sum of your energy forever. But that's only true when there's no external input or output of energy. And this is just in a closed system. So now we get to systems that are not closed systems. Addition or subtraction of energy to or from a system. So just to jump ahead, I've added one thing to this formula. This is the potential energy the conservation of energy formula before. But instead of just saying KE plus PE initial equals KE plus PE final, there's also this WNC, which stands for non-conservative work, or work done by a non-conservative force. And like I was telling you, if you look up the definition, you're going to find some hard to understand definitions. They're going to talk about reversibility and things being independent of their paths and stuff like that. But basically, if you have a force, or if you have work that's adding energy into the system or taking energy out of the system, then it's non-conservative work. And one example is friction. Friction's always going to give you negative work. It's always going to steal energy from the system. But you can also have something like a motor or a person who's pushing on something and giving it energy. So this can be positive too. All right. So this is just an example to show how you can apply this. And I think you could probably do everything we're going to do here using some other stuff I've already showed you, but this is just another tool in your toolkit. We've got a 20 kilogram child sitting at rest at the top of a slide. I'll just draw the picture. Here's the child right here, and the velocity is 0 meters per second. And the slide's 5 meters long and 3 meters high. So this is 3 meters. This is 5 meters. You don't really need to draw a picture. I'm just trying to make it easier to understand. As the child slides down the slide, the child experiences the constant 5 Newton force of friction. So the child's going to go down the slide. The friction's going to be up the slide. First question is just something we've done before. The child's total energy at the top of the slide. What form of energy does the child have? Well, we've got two choices. We've got potential energy. Actually, I'll just write PE plus KE equals the total. And screen went off again. Does anybody know, of those two, which one would the child have at the top? PE, no KE. If you calculate PE, it's MGH, and the child does have some height. Oh no. I'm going to come up with a different solution here. I don't want to. I'm going to do a Mr. Ferris. He just gave up, right?
Because you guys talked about something totally unrelated.
Yeah, I need to let me just tell you a story. No, I'm going to just work on, I do not want to disconnect shut down my computer and then start it back up. So, let's see. I'm going to do, I guess I'll turn off that projector. Ooh, I wonder if turning off the projector and turning it back on would work. I'll try that sometime, not right now. So I'm just going to, I know you've got your paper, and I've got my paper, and I'm just going to work on the board and write stuff. And I guess I can get rid of the extra window of me right there. That's a nice spot. So, here's my picture again. Here's the child. 2 legs. So at the top, the potential energy is MGH, and kinetic energy is 1/2 mv squared. And since the velocity is 0 at the top, this is 0, and this is just going to be the height of the slide, which is 3 meters, times 9.8, sorry, being messy, times the child's mass, which it tells us is 15 kilograms. Nope, 20 kilograms. I'm getting my problems mixed up. So sorry that's so messy, but it's 20 times 9.8 times 3, and I'm just cheating on my little cheat sheet over here. That comes out to 588 joules.
Wait, what's the last number?
3.
3.
This is the mass of the child, G, and then height. So 588 joules. That's the total amount of energy. This is all of the child's energy at the top. All right. So B is asking how much work is done by friction. So as the child slides down here, friction is going to push that way, So this is kind of a weird idea. The friction is pushing that way. As the child travels a distance this way, and we're told that this distance right here, from there to there, this is, let me just draw this, 5 meters. So even though it's kind of funny that the force is in the opposite direction that it's moving, it's still in the same dimension. So the work in B, the work done by friction, is the force of friction times the distance, and we're given that the force of friction is 5 newtons, and the distance is 5 meters, so it's 25 joules. Now, I could just leave it as 25 joules and say, let's just be really aware of what this is doing. Is this going to give the child energy or take it away?
It's going to be negative.
Yeah, so if we're calling this a positive direction, then we could say that the force of friction is really negative because it's pushing opposite to the motion, so that's going to be making the work done by friction negative. I don't care if you make it positive or negative, but I just want you to know that it's going to need to be subtracted from that total amount of energy that the child has. All right, so part C, this is where the new formula is going to come from, or come in. I'm just going to write the formula again, and we're asked how much potential energy and kinetic energy does the child have at the bottom of the slide. So the new formula says if you take the potential energy in the beginning, and you add that to the kinetic energy in the beginning, and you add that to the non-conservative work done. So any work done by some outside force, then what you will get is the final potential energy plus the final kinetic energy. So the total amount of energy here is going to be the same as the total amount of energy at the end, with the exception of any energy that was added to this or taken away from this. So in this case, this is going to be negative. It's the work done by friction. So in the beginning, the child had a potential energy of 588 joules and 0 kinetic energy, and the work done was 25 joules. It was negative work. It was taking energy away. And that equals the energy at the end. So here there's 0 height. So the potential energy is 0. And the kinetic energy, that's basically, we don't know that. We're looking for that.
Why not? Isn't it just the other side, so subtract?
Yeah,
Okay.
yeah. So you can solve for it, but I'm just saying, if I'm filling in all these things, I know this, I know this, I know this, I know this. I don't know the kinetic energy at the end. I don't know how fast the child is going to be going. But using this, then I can just do 588 minus 25 is 563. And that equals the final kinetic energy. So I think there's another way we could have done that, but hopefully, I mean, this formula is kind of nice. You could use it for all sorts of things, places where you would use the work energy theorem. And then finally D, this is kind of a letdown. What's the child's speed at the bottom? So we've got the kinetic energy. How do we get the speed? Anybody? Anyone from home?
Is it
1/2
mv
equals-
squared?
Yeah, so the kinetic energy is 1/2 mv squared, which is 1/2 times 20 kilograms times v squared, and that equals 563. So you multiply by 2, divide by 20, and then take the square root. V ends up being 7.5 meters per second. Plus or minus 7.5, but the minus 7.5 doesn't make sense for speed. All right, so that's how I use that formula. And what I would like people to work on now, I think we should do this together. And maybe while people are working on this, I'll give the projector another shot. I'll try to come up with something, because this is going to be hard for me otherwise. So what I want to do as a class is this. So in your packet, turn to page 4, and I want you to try to fill in this chart down here. In the past, I've given it kind of as a homework assignment, but we've ended up working on it together anyway, so I think this will just be a let's everybody do it together kind of assignment today. Let me set the stage for this. So it says that the diagram below shows the path of a 200-kilogram car on a roller coaster. Between points A and B, the car is pulled up a slope in the absence of friction. So this is whatever is raising the car up to the beginning. Now this next part, I kind of regret the way I did this. It says starting from rest at point A, the car is pulled up by an average force of, you can see the force, 1,120 newtons. That's the force that's pushing it up this 70 meters of track. When it reaches the top, its speed is slowed to 0. Oh, good. Never mind, I fixed it. This is all good. So its speed is slowed to 0. So it starts at 0, it gets E. Between D and E, a constant 500 Newton braking force, so that something's hitting the brakes here, slowing it down, is applied. But this is not enough to keep the cart from flying off the precipice at E. Complete the table. So you're given the height at point B, it's 90 meters, and you're given the velocity at A and B, and you have to fill in everything else. I'm going to futz with the projector, and hopefully I can get it going again. Worst case, I'll just have to restart my computer. I don't think it's going to work, though. I think I have to shut my computer down. But I don't want to. Okay, I'm just not going to. I'm going to recreate the table on the board. Okay, I've got everything recreated up here. I'm wanting people to help me on this. Just tell me what you've got, and I'll tell you if you're right, and then we'll talk about how to solve each of these parts. There's one part of this that I think is hardest. I think it's actually the height at A. I think that's one of the hardest things to find. This looks like it says AV. Let me fix that. All right. So I'm going to call on people, and if you have something that I can fill in, tell me what it is. Sam, you have anything?
I think the potential energy for B is 176,400 joules.
Yes, 176,400 joules is. And I guess I forgot to label up here the car mass is 200 kilograms. So at B, you can use, or any time that you have this, you can use MGH. So we've got the car mass, 200 kilograms, times 9.8, and we know the height is 90, so that's got to be 176,400. Canizaro, do you have anything?
I did not get to go.
Do you have anything else, Avery?
Height at sea is 60 meters.
Height at sea is 60 meters, yes.
Oh, I did get heights. That's good.
And how did you get that?
They gave you the height from B to C is 30 meters.
Yeah, so 30 meters, so you just take off 30 from 90, 60. Let me pick on somebody from home. Carlota, do you have another number I can fill in?
I'm not.
No? How about Sarah?
No.
Sarah, do you have one? What? Guess it was a no. Julia. Maddie? Jack again.
Alright, height for D is 60, E is 60, and F is 30.
Oh, wow.
Yeah,
Got all the
nice.
numbers, dude.
60, 60, 30.
Wow.
Yeah, excellent. Yeah. Those are all the same. And then this is 30 lower. So we're good. Those were low-hanging fruit. Somebody should have nabbed those before Jack. So, Ollie, do you have anything else to add on?
No.
Reese?
He really took all my numbers.
Does anybody from home have anywhere we can go next?
Oh, the total energy for B would be the potential, right?
Total energy where?
For B.
For B? Yes. Yes. So, and that means you know one other one. So that at B, why is the total energy the same as the potential energy?
Because it's not moving.
It's not moving, so what else do we know there?
There's no kinetic energy.
Yeah, the kinetic energy is 0.
Oh.
So that should give some people some more ideas. What else can we fill in? People at home, if you want to blurt out, you can. You can think of something else to add. Oh, Julia.
Why is your total, like, for the 400 and like, not?
Oh, because I am not good at attending to details when I'm in front of class. Yeah, Avery?
The kinetic energy for A would be 0.
Yeah, kinetic energy for A is 0 because the velocity is 0. Oh, and this. So this, anytime we have anytime we have the velocity, we can get this. And anytime we have this, we can get the velocity. Anything else we can do? Let's see, is there more information? Oh, there is some information. Between here, there's this force which is 50 newtons.
I think it's 500.
500?
Wait.
No, it's
Yeah.
Yeah, it's the
500.
braking force is 500 newtons.
Oh, did I say 50 and 500? Oh, this is the old one. This one must be wrong. Okay, good. I'm looking at an old copy of this thing. I hope all the answers are the same. They probably are. Probably just had it wrong before. Anyway, we'll figure it out. What else? Sam?
The potential energy for C, D, and E is 117,600.
Yes. And we know that because it's, we can just use MGH. So the height's 60, that'd be the H. G is 9.8, and the mass is 200. Anything else? This one seems to be kind of an easy column. In fact, keep going there.
F is 58,000.
58,800. What's that? Yeah, MGH. So anytime you know the height, and you know the mass, and you know G, then you've got potential energy. All right, so let's forget about that, because I mentioned that's a hard one. And this, we can't really get until we get that. I mean, or those will kind of go together, so just leave those alone. Of these three remaining columns, guess which one we have to go after next?
Velocity. Right?
How can you?
Kinetic
Yeah, if we had this, then we could get that. So I don't think there's any way to directly get velocity because we're not given distance and time. You can't use kinematics. So we'll have to do this before that. And I don't think we can do the total until we've got kinetic energy. So that's where we need to go next. So we need the kinetic energy here, and here, and here, and there. Now, all right, I don't want to give any hints. I want somebody to figure it out. Let's figure out somebody figure out the amount of kinetic energy at C. And I want to remind you that there's no friction between here and D. The friction only begins between D and E. And then there's no friction again from E to F. Actually, you know what? I lied. So this isn't actually the easiest column to do. It depends on how you approach this. This is the easiest column. So
Isn't it just addition for that column?
what's that?
It's just addition.
It would be, maybe. Yeah, it is addition. So if you knew this, you could add these together to get that. But you can get this without knowing what that is. So at B, let me just reiterate what's on here. At B, the potential energy is 176,400 joules. There's no kinetic energy. The total energy that it has there is 176,400. When it gets to C, as it travels from B to C, there's no friction. Yes, Avery?
The total energy is going to be the same for B, C, and D.
Yes.
Because there's no friction, so that means that no energy is leaving.
Yeah, so energy is conserved. If there's no external input of energy and there's no output of energy, if there's no friction stealing energy away and there's nothing else adding energy to the system, these are going to be the same. So between B and D, there's no friction, so the energy is conserved. So the total amount of energy is going to remain the same all through there. It's just going to change. At B, there's a whole bunch of kinetic, but then, a whole bunch of potential, but when it gets to C, there's going to be less potential, but now more kinetic. So, but things change at D. At D, this isn't going to stay the same anymore because friction is going to start drawing down the total amount of energy. So what's this? No.
Oh, wait. I read it wrong. 200.
Somebody do the math on that.
58,000.
Yes. So this is the total energy, and the total energy equals the sum of those two. So what happened between B and C is that some of this potential energy went away, and an equal amount of kinetic energy appeared. How about the kinetic energy at D? Now that we know the kinetic energy at C, guess what it's going to be at D? The same, because there's no friction here, and it's not going up or down or anything, so it's just going to be the same speed and all that. Sorry, I'm so messy. So now there's a kind of an easy thing we could do.
Solve for velocity.
Yeah,
Same
so we can use this formula and solve for velocity. So it'd basically be kinetic energy times 2 over m square root of all that. Does anybody want to try that on this? If you take the kinetic energy, I think that's right. Did I do that right? If so, ke times 2 divided by m, take the square root. Anybody at home? Can you calculate what this velocity would be? Should be the same as
24.24.
24.24, yeah. Just going to call it 0.2. And the same here. All right. Now, E. When it gets to D, for the next 40 meters, there's going to be a force of friction of 500 newtons, or I guess we could say negative 500 newtons, because it's opposite the way it's moving. What's that going to, yeah, Sam?
Is the total energy going to be 156,100?
Yes, yeah. And I'm going to write out the equation for that using I'm just going to write out the law of conservation of energy with non-conservative forces. But the thinking there is friction is a non-conservative force which either adds energy into or takes energy out of a system. In this case, it's taking energy out. So the total amount of energy is going to decrease by the amount of work done by this force. It's a 500 Newton force multiplied by a 40 Newton distance. So you get 20,000 joules that need to be subtracted. So the more legit way to do this, if I wanted to compare D and E, I could say potential energy at D plus the kinetic energy at D plus the non-conservative work done equals, if there is any. You could always use this formula and just say, there's no non-conservative work this time. Equals the potential energy at E plus the kinetic energy at E. And the potential energy at D I knew was 176,400. The kinetic energy at D was 58,000. And then the work was negative 500 times 40, so minus 20,000. And that equals the potential energy in kinetic. Now the potential energy is going to be the same as it was before because the height hasn't changed here. So the potential energy is still 176,400 plus the kinetic energy. So using this, I can actually solve for kinetic energy. So kinetic energy is 176,400 plus 58,000 minus 20,000 minus 176,400. So really I could just remove those from both sides of the equation, subtract there, and I get 38,000 for this. And now that I know the kinetic energy, what do I do to get velocity?
Just that formula.
Yeah, basically use this solving for velocity. And that comes out to, I got 19.7. Somebody should check me.
Yeah. Shouldn't the kinetic energy be 38,800?
Yes, yes. Thank you for attending to details again. 38,800. And then finally, between E and F, I think it says there's no friction. Yeah, it doesn't really say, but let's assume there's no friction as it's flying through the air. So which one of these can I do next? If there's no friction. What's that?
Total energy.
Total energy will be,
Same as E.
yeah, the same. Because the total energy is going to be conserved. We're just going to be changing one kind of energy for another. So if this is the potential energy, how do I get the kinetic? Subtract that minus that, and that should be, check my math because I screw up, 97,600 is what I have. And then we can get this by multiplying this times 2, dividing by the mass, taking the square root, that should be 31.2. And now we've got the hardest ones left. The at point A, the height, the potential energy, the total energy. And the key here is that there is a force, there's some kind of lift mechanism that's applying a force of 1,120 newtons the whole time between A and B. And then it stops. So 0 velocity here, 0 kinetic energy here, but we don't know the height, we don't know the potential energy, we don't know the total energy. Anybody have a suggestion? Yeah, Jack.
Don't we know the potential energy and the kinetic energy of B? So can't you use that? Because isn't that at the top?
We know the potential and kinetic here.
Yeah, so isn't that like the final for the...
Are you suggesting we use this formula?
Yeah.
Yeah, there we go. So if we use this formula, instead of going from D to E, let me erase these letters. So this is going to be, we're just comparing the event of it traveling from A to B. So if we take the potential energy at A plus the kinetic energy at A, plus the work that's being done on this, that should give us the potential energy at B plus the kinetic energy at B. Potential energy at A, do I know that? No. So I'll just leave that. PE, A. Kinetic energy at A is 0. The work is just going to be this force times 70 meters. That's the extra energy that's being put into this as it's being lifted. And that equals the potential energy at B, which is 176,400. Plus the kinetic energy at B, which is 0. So basically, 176,400 minus whatever the product of those two is, that's going to equal the potential energy at A. Has anybody calculated that?
Did
Yeah.
it say that it was pulled up the slope? Never mind. Never mind. I thought I read that it said that is in the absence of friction.
Oh, well, it doesn't.
Wait, no,
Yeah, it doesn't-
between points A and B, the car is pulled up a
Yeah.
slope in the absence of friction.
Yeah, so there's positive work being done on it here, but there's not any negative work to worry about. So anyway, has anybody calculated what PEA is?
75,000.
75,000?
I did 97 right?
Yeah, I got about 98,000
Yeah.
when I did it before, but I could have done it wrong. PEA is somewhere around 98,000. It's okay. I make mistakes too, as you all know. 98,000. All right, so what's the easiest thing to fill out now? Of the two, which one's easiest? Total is going to be that plus 0. And then the height, how do we get that?
Divide by the mass and
Yeah, divide by mg. So if this is mgh, divide by m, divide by g, and what's left over will be h. So that divided by 200 divided by 9.8 again gives us 50 meters. All right, that was a good exercise, I think. And since I guess I just get to stay up here, this is making me happy because I told you I've been reading this book, that sitting too much is killing me. So the next 2 pages, 5 and 6, that's your assignment. And anybody who's retaking the test tomorrow, if you want to if you need to focus on that and you don't get this done on time, that's okay, but try to keep up. So I made a couple of videos for this too that are linked in Google Classroom and on my website. So that's it. Any questions from the people at home before I shut you off? All right, I'll see you all later.
Thank you.
You're welcome. People in here, this is just work time. Yep.